All right. This is a practice final exam version 2. And if you look at the video description below, you'll see the timestamp for each problem. So if you click each one of those, you can directly jump to the corresponding problem. So let's start with a problem number one, part A. Suppose you are given those 3 points in the xyz space are 3, and then find those 2 vectors. So remember how to find, so to speak, displacement vectors between 2 points. So schematically, suppose this is point A and this is point B, and then you have the origin, and then if you look at those 2 vectors, the vector OA is the position vector of the point A. So that vector has the components which are the same as the coordinates point A, and similarly for B. And then vector AB is, from this picture, written as OB minus OA. So that means what you do is basically subtract coordinates of the second point, first point from the second one minus the first one. So in this case, it's written like this, and then this is actually 2, 1, negative 1. And similarly, if you have a AC, the vector AC is OC minus OA, and that is OC has a component the same as the coordinates of C, and the OA is as before, and then this gives you 0, 1, negative 2. Part B, compute the cross product of those 2 vectors you obtained in part A. So it's a cross product, so the answer is AB cross AC is IJK, and then you list the components of AB on the second row, and the components of AC on the third row. And that is equal to, for the first component, look at I and then eliminate all those 1, negative 1, 1, negative 2, I. Then the middle one is minus. Now you look at the middle guy and eliminate all those. So 2, negative 1, 0, negative 2, J, plus, finally, the third component is look at the K and hide those. And then what you're left with is K. All right. And then this is equal to, you multiply diagonally and subtract one from the other, minus 1, I, minus negative 4, negative 0, J, plus 2 minus 0, K. And that is equal to negative I plus 4J plus 2K. So that's the answer. Part C. Find the equation of the plane that contains those 3 points A, B, C. All right, so to find the equation of a plane, what you need is 2 things. 1 point the plane goes through, and the vector which is perpendicular to the plane That's what's called a normal vector. Then now, in this case, points A, B, C are given, and the plane contains all 3 points. So you may use any one of those as your one point that plane goes through. So the only thing you need is a normal vector. But normal vector is a vector perpendicular to the plane. And in part C, you computed cross product of AB and AC, and indeed that vector, namely this one, serves as a normal vector. You could use this as your normal vector because, let me just write down a schematic picture. So suppose this is a plane, the plane that contains ABC. Let's say A, B, C. And then in the previous problem, we computed the cross product of vector AB and vector AC. And then the cross product, so that means those two vectors are on the plane. And then the cross product of two vectors is a vector perpendicular to both of the planes, like this. So therefore, we could use this one, AB cross AC, which we computed as negative I plus 4J plus 2K is our normal vector, is a normal vector. And then, like I said, as your point, you could use any one of those. Let's use A. It doesn't matter which one. Negative 1, 0, 1. Okay. So that means the plane we are looking for has this as a normal vector, and it goes through 0, negative 1, 0, 1. So therefore, the equation of the plane is negative 1, x minus 1, x minus 1, plus 4, y minus 0, plus 2 comes from here, and z minus 1 is from here. And that is equal to 0. Okay. And then if you simplify this, you'll see x minus 4y minus 2z plus 3 is equal to 0. So that's the answer. And if you use B or C instead of A here, if you use B or C instead of A, then you'd plug in different numbers here, here, here. But if you simplify everything, you are supposed to get the same thing. Okay, so it doesn't matter which one to use. Anyhow, so that's the final answer. Now, problem number 2. Let f of x be this function, e to the power of xy plus x squared. And then compute those. So those are partial derivatives. So what you do is to compute those partial derivatives. And now, f sub x, this means the partial derivative of f with respect to x. So what you do is to differentiate this with respect to x. So this is e to the power of xy plus x squared. So you use the chain rule, basically. And then you have to multiply the derivative of whatever you have for the exponent, but you have to differentiate this with x, and get y plus x, y plus 2x. I'm sorry. I copied the problem wrong. This is y squared. Sorry about that. So you multiply the derivative of this with respect to x. So that means you multiply y. This should be written as xy plus. So this is y squared. And then now fy is the same thing. since it's an exponential function, you just keep this, and then you multiply the derivative of this with respect to y. So x plus 2y, and I is equal to okay. And then now fxy, that's the derivative of y, derivative of f sub x with y. So you differentiate x sub x with y. So you differentiate this with y. And then what do you get? Since it's a product, you have to use the product rule, and then derivative y is 1. So just this. And then now keep y, and then you differentiate this one with y, you get e to the power of xy plus y squared, and then you multiply the derivative of the exponent with y, and get x plus 2y. All right. And this is okay, but it's better to simplify it. And if you simplify it, this is written as 1 plus xy plus 2y squared e to the power of xy plus y squared. Then now, you want to compute this. But this one, you may just directly compute it by differentiating this, well, maybe this with x, but we know that this one is actually equal to this. So you don't have to do the calculation. You could just do like y f xy, and the same thing. The answer is the same. xy plus 2y squared e to the power of xy plus y squared. So that's the answer. Part B, compute this directional derivative where f is the same as the previous one. So f is this f, the same f. And then the direction u is here. All right, so here's the answer. To compute directional derivative, and you have to, by the way, plug in 1, 0. So to compute directional derivative, you have to compute the gradient. That is fx, fy, and that is, well, we already computed those two derivatives in the previous part, here and here. So let's use those. And then this is y e to the power of x plus y, y squared, x plus 2y, squared. Okay, and then, so that means if you plug in 1, 0, let's just plug in 1, 0 at this point, and then just plug in 1, 0. The y is 0, so it's 0 and 1, 0, 1. Then, so therefore, the directional derivative is computed as the gradient dot the vector that gives you the direction. So in this case, 0, 1 dot 1 over root 2, 1 over root 2, and that is equal to 1 over root 2. So the answer is 1 over root 2. All right. Number 3, let f of x, y, z be this. So it's a function of 3 variables. Now compute, first part A, compute the gradient of f. So here's the answer. Gradient of f is f sub x, f sub y. And since we have 3 components here, x, y, z, we do like this. And that is, so you differentiate with x, you get y z squared. And if you differentiate with y, you get xz squared, and you differentiate with z, you get 2xyz. All right, so that's the answer. Part B, compute the divergence of the gradient f, where the gradient of f is as computed in the previous part. So remember, divergence means that means that you just differentiate each component of the given vector field in this case. So in this case, this component, this one, each component with the corresponding variable, and then you differentiate each component with the corresponding variable, and then add them all. So this is partial x. And then you differentiate yz squared plus partial y, and you differentiate xz squared plus partial z, 2xyz, and this is equal to 0 because no x appears here. And the second term is also 0. And the third term, you differentiate with z, you get 2xy. So this is equal to 2xy. Okay, so that's the answer. Part C, compute curl of the gradient of f, namely compute the curl of this vector field. So here's the answer. Curl of the gradient of f, that is, this is often written as nabla cross product. What are the vector field you take the curl of? And then, so it's a cross product. You do like I, j, k, and the partial x, partial y, partial z. And then you list the components of the vector field you want to take the curl of. In this case, those. If you do it, you get yz squared, xz squared, 2xyz. And I take the cross product, take the determinant of this, and so that is equal to first component, partial y, partial z, xz squared, 2xyz, I, minus partial x, yz squared, partial z, 2xyz, j plus partial x, partial y, z squared, xz squared, k. Okay, and then you do like this. But when you multiply those two, this means basically you interpret this multiplication as differentiation. You differentiate with y in this case. So in this case, you have 2xz minus, you differentiate, you get 2xz. They get cancelled out and you get 0. And then do the same thing here. 2yz minus, you differentiate with z, 2yz again, j. So they get cancelled out, you get 0 too. And then finally, you take care of the last term, you get z squared minus z squared, k. Now this gets cancelled out too, so what you get is after all 0i plus 0i, 0j plus 0k, 0, 0, 0. So this is, so to speak, 0 vector. So the answer is 0 vector. That's fine. That's the final answer. But this is what's supposed to be. So in general, not for this example, but in general, let me just mention it. If you take the curl of the gradient of some scalar field, this is always 0. Okay, it's a theorem. You can easily prove it, but it's a theorem. So for this problem, if you know this theorem, or if you quote this theorem for your answer, you don't really have to do this calculation. But you could just say, okay, compute this. You can just say, oh, that's 0. But anyhow, so that's the answer for part C, number 3. Number 4, part A. Evaluate this double integral where D is given by this region. The picture is provided. It's a region bounded by y is equal to root x and y is equal to 1 straight line and the y-axis. All right, so this is a straightforward problem for double integral. So remember, when you compute double integral, you pick up one of the variables which you integrate first, meaning that you fix the other variable. And in this case, it doesn't matter which one to fix first, but probably it's easier to fix x first. It doesn't matter, like I said. And for each fixed x, your y value varies from this parabola y is equal to root x. That's the starting point for y for each fixed x, all the way up to y is equal to 1. So this is y is equal to 1. So the given integral is written as, you fix x and you integrate with y, and y is, like I said, root x and 1. Okay. And then you integrate with x, but the limits for x are from 0 to this point is 1. So this smallest possible x is 0, and the largest possible x is 1. So the limits for x are 0 and 1. Okay, so all you have to do is just work this out. 0, 1. Then now you integrate y, and then now y is from root x to 1 dx, and I is equal to 0, 1. 1 half minus 1 half x dx. And then now this is just a calculus one, and then this becomes 1 half x minus 1/4 x squared and 0, 1. And if you work this out, you are supposed to get 1/4. So this is the final answer. Problem number 4, part B. Evaluate this double integral where D is the region given here. But to be precise, everything inside this disk, half disk, semi-disk, whatever they call it. This part. So this is a typical problem for using polar coordinates. So let's use polar coordinates. By polar coordinates, x is r cosine theta, y is r sine theta. And then for polar coordinates, you often see expression like this one, x squared plus y squared. And then that is always r squared. So this is part of the formula for the polar coordinates. And then dA becomes r dr d theta. Don't forget this r. All right. And then now you have to find the limits. Since this is everything inside radius 3, the radius r is between 0 and 3, and the angle theta is between 0 and pi. So all you have to do is just plug in those to here. And then what do we have? So therefore, we get integral cosine x squared plus y squared, that's r squared. And then dA is r dr d theta. And then r is between 0 and 3. And theta is between 0 and pi. And this becomes what? 0 pi. Then now if you look at the inner integral this part, or maybe this part, you will see that this is indeed 1/2 sine r squared. And then r is from 0 to 3. If you differentiate this, you get this. All right, and then this is 0 pi and 1/2 sine 9 minus 0, that's 0, so minus sine 0 is 0, so 1/2 sine 9 looks strange, but that's okay. D theta, I forgot D theta here. And then you integrate with theta from 0 to pi, but this is just a number, right? This is just looks strange, but it's not a variable, it's just a number. So this becomes sine 9. Right, so that's the answer. Number 5, let S be the surface of the cylinder. X squared plus y squared is equal to 9. So it's radius 3, it's cylinder. If you just look at this on the xy plane, that's a circle with radius 3. But if you look at on the xyz space, that's a cylinder. Just like cylinder goes like this. It's like a cylinder with radius 3. And then you look at the portion where z is 1 between 0 and 1. Then now find the parametric equation RUV of S. Namely, you have to parameterize the surface of the cylinder and sketch its domain on the UV plane. So since it's a circle for the xy, we could use polar coordinates for xy. So x is 3 cosine u. So u is one of the parameters, and y is 3 sine u. And then z is what? Z is just a v. Okay, so that's the way to parameterize a cylinder. So to be more precise, R of uv is written as 3 cosine u. So that's the first component, I component, and j component or y component is y, and then z is v. So that's the parameterization. And then you have to sketch the domain. What do you mean domain? Domain means all the possible regions where u and v can take in order for you to be inside the surface of the cylinder. So of course, u is just an angle. So u is between 0 and 2 pi. And then v is what? V is z. Z is equal to v. And z is between 0 and 1. So v is between 0 and 1. So on the UV plane, what's this? This is just a rectangle. UV plane. Two pi 1. And this portion, this shaded region. So this is our domain. Part B, compute RU cross RV, where of course R is the same as the previous program. Now, what was this? This one, you take the cross product of two vectors. So you write I, J, K. And which vectors? Well, RU and RV, but what's RU? This is the derivative of this one with respect to u. So you differentiate it with u. And what do you get? You get negative 3 sine u. We just need more space. And then 3 cosine u. And if you differentiate v with u, you get 0. And then now, RV. Oops. Now RV, you differentiate that with v, you get 0, 0, 1. And then you take the cross product. And if you work this out, you are supposed to get, I'm gonna omit the middle computation, ui plus 3 sine uj plus 0k. That's what you get. All right, part C, compute, evaluate this surface integral of the vector field F, which is given this way, where S is given inward orientation. Then now, let's remember the formula says F is whatever the region on the UV plane you plug in the parameterization to the vector field you integrate and dot du dv, or this could possibly be negative, or maybe I should say the other way around, v cross u. Either way, and which one is right depends on what the orientation of S is. Then now, everything is given in the previous part, and the only thing you have to check is the orientation given by this vector, this cross product, namely this one, is consistent with the given orientation of S, in this case, inward orientation. Now, how would you check? Well, what you typically do is just pick up a test point, so to speak. So in this case, let me just write down the picture here. This is the surface of the cylinder, and then the given orientation is the inward orientation. So orientation is pointing this way, up, or like this way, like this. Then now, to check if this one gives the right orientation or not, what you do is to pick up one point, like I said. For example, let's pick up u is equal to 0. Okay, that's, and z or v is equal to 0, but it's independent of v. But anyway, if u is equal to 0, this vector gives you, so this vector gives you, at u is equal to 0, what do you get? Well, you get 3, 0, 0. 3, 0, 0 is the vector. So u is equal to 0 corresponds to here. So u is equal to 0, v is equal to 0 corresponds to this point, because u is the angle and v is the height. And then 3, 0, 0 is a vector going this way. So it's outward. So this means from this little computation, you will see that this guy here, this guy here gives an outward orientation, but this one is an outward orientation. So it's the other orientation than the given orientation. So what you want to compute is negative of this. So that's the answer. So you have to put the negative sign, because maybe I don't need but because of this remark in the parentheses, you need negative sign. If this were if S were given outward orientation, then in that case the orientation of RU cross RV would be consistent with the orientation. So therefore you don't need negative sign. Anyhow, so all you have to do is just compute this. What's this? D. Let's just keep D here for now. And then you plug in parameterization to the integrand and take the dot product with that. Then you get, well, let me just, it's okay. Then that is this. Let me just write it out here. 3 cosine u I plus 3 sine u j plus, here you have to multiply all those three. So that is 9v cosine u, sine u, k, and you take the dot product with this vector, and that is the same as this one here. Fortunately, the last term is 0, so you get some cancellation. But anyhow, 3 cosine u I plus 3 sine u j plus 0k and du dv. And then if you take the dot product, you just multiply those. Oops. You just multiply this, and 0 times this. And if you carry that out, you get 9 cosine squared u plus 9 sine squared u plus 0. And now, cosine squared plus sine squared is equal to 1. Oops, I forgot negative sign here, sorry. This negative sign has to be here. Sorry about that. This is, we need negative sign here, and that is equal to negative double integral 9 du dv. Now what's d? Well, this is of course written as d du dv, and this double integral gives you the area of d. So this is simply just negative 9 times the area of d. But what's the area of d? D is indeed the domain for u and v, namely this rectangle. So that's d. Okay, d is here. Let me just write it down. Oops. D is simply what you get in part A 2 pi and 1. Like this. So therefore, this is just, the area is 2 pi, so this is a negative 18 pi. So that's the answer. Number 6, evaluate this triple integral where E is the region between those two spheres. It's a region sandwiched by those two spheres. Sphere with radius 1 and a sphere with radius 2. Okay, so it's a typical exercise for triple integral using spherical coordinates. So by the spherical coordinates, spherical coordinates. What? Well, actually, since the integrand has only z, we only need z for the formula. Z is rho cosine phi. Strictly speaking, we have x and y, but we don't need x and y for the sake of this problem. And dv is, this is important, rho squared sine phi, d rho, d phi, and d theta. Now you have to find the limits. Now the radius rho is what? It's between 1 and 2. Sphere with radius 1 and radius 2, so it's between 1 and 2. And then theta is between what to what? Well, actually, sorry about that. I missed one more condition. It's a sphere between those in the first octant. Sorry about that. I missed this. So first octant means only this part. So we are looking at only this part. Like this part. So that means the theta is the angle from the x-axis. This angle is the theta. So theta is between 0 and pi half. And then phi is the angle from the z-axis. That's phi. So in this case, it's also from 0 to pi half. So those are the limits. So therefore, the given triple integral is obtained by, now, like I said, z, the integrand, is here, rho cosine phi times dv is here, here, rho squared sine phi d rho d theta d phi d theta. And then now, limits for rho is from 1 to 2. The limits for phi are from 0 to pi half. And the theta is also from 0 to pi half. Okay, and then this can be actually rewritten as, if you just group together the variables, rho's are here, d rho, times a theta is just d theta. There's no theta appears in the integrand. And then phi is cosine phi sine phi d phi. All right, and if you work this out, so this is the integral. Calculus 1, you know how to integrate this, And this one, it's your exercise. In any case, if you carry out the integration, you get this. So that's the answer. Number 7, part A. Find the parametric equation of the curve y is equal to x squared. All right, so in general, if you have y is equal to f of x, so it's a general formula, x and y like this. And then there's a canonical way of parameterizing this curve, namely you use x your parameter, namely t is equal to x, or x is equal to t. So x is t, and then for each, if x is t, in order for you to be on this curve, your y value has to be f of t. So this is the canonical way of parameterizing a curve given by y is equal to x, f of x. And then if you are specified some finite region for x, t would be a and b, like this. So that's the general formula. And this is just a special case. Our problem is a special case. And this problem, it doesn't specify the range for t. So the answer is, after all, so this is just a remark in parentheses. So the answer is, R of t is t, f of t, but f of x is x squared, so this is t squared. Now, part B, evaluate this line integral where c is as above, namely c is this parabola starting from 0, 0 and ending at 2, 4. And if you look at the integrand of the line integral, you'll see dx, dy, both dx and dy. So this is a vector field, okay, a line integral of vector field where the vector field f is y and x. Okay. Now, so for this, so like I said, our f, or f of x, y to be precise, the vector field we integrate is x. And for this, first you parameterize the curve, but we know how to do it. It's already given here. And then what you do is to compute the derivative. So you differentiate component by component, like this. And then what you do is to compute f of r of t. What does that mean? That means you plug in the parameterization to f here. What does that mean? That means in this case, you set x to be t and y to be t squared. So y is t squared and x is t. All right. Then, so therefore, the given integral is computed as integral of f of t dot the derivative dt. Then now t is from where to where? Where t is x and x is from 0 to 4. So in this case, t is from 0 to 4. So like I said, just like this, x values. Those are the limits. All right, so what's this? This one is 0 to t squared t dot 1 to t dt, and that is equal to 0 to t squared plus 2t squared dt. You take the dot product, and that is equal to 0 to and 3t squared dt. And if you work this out, you get 8. So that's the answer. Number 8, evaluate this line integral where our C is the region bounded by two parabolas like this, but the direction of the curve is clockwise instead of counterclockwise. And now, actually the problem says use Green's theorem. So we're going to use Green's theorem. What's Green's theorem? Let P is equal to PB. Whatever you see in front of dx. And then Q is 2x plus e to the power root y. Then, typically, Green's theorem says, by the way, this little circle is to emphasize that the line integral is over a closed curve. Green's theorem says this double integral, and d is everything inside C, and partial q, partial x minus partial p, partial y, and dx dy, or dA. So that was Green's theorem. But, so this is Green. But this is the case if the direction of the curve C is counterclockwise. But for this problem, it's actually clockwise, the other way around. The orientation is the opposite. So in that case, you have to put negative sign because the orientation is negative, so to speak. So in this case, this is equal to negative d, and d is, of course, by the way, this everything inside, that's our d. And then you compute this. What you get? You differentiate that with x, you get 2 minus, you differentiate this with y, you get 1. And dA. Okay, so then this is equal to negative d dA. And so this is just the area of this shaded region. So you could use it, you could compute it by even calculus 1. But let's just do it with a double integral, just as an exercise. Oops. Let me just move it. All right, so this one is, so to compute double integral, you fix one of the variables and integrate with the other variable. And in this case, let's fix x. And for each fixed x, your y varies from this parabola to the other parabola. So the bottom parabola is y is equal to x squared. And top parabola is this one. That is y is equal to root x. So the limits are from x squared to root x dy. And then x is from 0 to 1. Of course, the point of intersection is 1, 1, so it's 1. So you integrate x from 0 to 1 dx. All right, and then I'm not going to do the detailed calculation here. You can just verify that this gives you 1/3. Number 9, part A. Let S be the part of the sphere x squared plus y squared plus z squared is equal to 5. So that means radius is root 5. But we look at only the portion where z is above 1. So the picture is like this part. It's like a little cap or whatever they call it. And then now the orientation is upward. So the orientation of the surface is upward orientation. And now, part A, find the parametric equation of T of, remember this symbol, this is the boundary of S. What's boundary? Boundary is this portion. This part is the boundary of S. Okay, so what is this boundary? Well, boundary is the circle floating in the air at z is equal to 1. Okay. Z is equal to 1, but what's the radius? Well, to find it, you plug in z is equal to 1 to here. So if you look everything from the above, the circle is at z is equal to 1. This one, and then this gives you, by simplifying this, you get 4. So this is a circle with radius 4 if you look at it from the above on the xy plane. So it's a circle with radius 4. So it's a circle. X is 2 cosine t. And then y is 2 sine t. Since our parameter is t, we use t. And then z is always 1. Okay. So it's a circle floating in the air at height z is equal to 1. Okay, so that's the parametric equation. Then now, how about the orientation? Is the orientation positive or negative? Well, to find the orientation, what you have to do is to use the right-hand rule. So your thumb represents the orientation of the surface. And the 4 fingers of your right hand correspond to the orientation of the boundary, orientation of the curve. And if you do this with this picture, what you should see is actually thumb up, right? And then 4 fingers are curling in this direction. Your 4 fingers are supposed to be pointing this direction. So that means if you look everything from the above, what you see is this with radius 2. So this is counterclockwise. So the orientation is positive. Remember, counterclockwise orientation is a positive orientation. So the orientation is positive. So that's the answer. Part B. Let F be this vector field and evaluate this surface integral by using Stokes theorem. So, what was Stokes theorem? Stokes theorem says if you want to compute the surface integral of a curl, then this is written as the line integral of the boundary of f, provided that the orientation of the surface and the orientation of the boundary match up. In other words, the orientation of the boundary is, so to speak, the induced orientation of the orientation of the surface. Then now, so that means the good thing about Stokes theorem is that if you use Stokes theorem from this direction, like in this direction, oops, today's stylus is not that good actually. Anyway, in this direction, you don't have to compute the curl of this, but you could just directly use this vector field to compute the integral. Then now, but by the previous problem, we know that orientation of the boundary is positive. So it's like, this is our boundary. It's a circle floating in the air. Then now, so to compute, so all you have to do is just compute this line integral. But to compute the line integral, you have to parameterize it. And we know how to parameterize it. So the boundary of S is parameterized by, let me just copy it from the previous part, 3 cosine t, oh no, 3 actually, 2 cosine t, 2 cosine t, 2 sine t, and it's floating in the air at z is equal to 1. Okay, and then to compute the line integral, what you do is to compute the derivative, negative 2 sine t, 2 cosine t, and 0. Okay, if you differentiate 1, you get 0. And then you have to plug in the parameterization to the vector field you integrate. So you plug in r of t to this f. Plug in the parameterization. So x is x squared. So x is 2 cosine t. So this is 4 cosine squared t. You take the square. And the second term is y sine t times z squared minus 1. So this becomes actually 0. And then e to the power of x squared plus y squared. But this is actually 4. So you get this. All right. Then this is, you can simplify it as 4 cosine squared t 0 e to the power of 4. So therefore, the integral f dot dr is integral f r of t dot the derivative dt. Now, what are the limits for t? But t is, remember, if you look at t from the, if you look at the boundary base from the above, it's a circle, and t corresponds to the angle. Like we are using t as the angle here. So it's from 0 to 2 pi. You just go around the circle. What's this? This one is 0 to pi 4 cosine squared dot negative 2 sine t t. And then if you work this out, since you have 0 here, I get cancelled out, and this you get 0. So this is quite simple, or this becomes quite simple. And then you get negative 8 cosine squared t sine t. Sine t dt. And then this one, you can use, actually use substitution. U is equal to cosine t. Anyhow, and then if you do this, you actually get 0. The answer is 0. So that's the final answer. All right. Finally, this is the last problem, number 10. Let S be the surface of the solid bounded by paraboloid and z is equal to 1 on the first octant. And this is a closed surface. Okay, it's not just a part of this paraboloid. It consists of 1, 2, 3, 4 different pieces. It's a closed surface. And then the orientation is negative. What does that mean? Negative means inward orientation. Negative was the same as inward orientation. And then now, let's compute the line or surface integral of vector field, where the vector field is given this way by using divergence theorem. So this is in a way a straightforward exercise by using divergence theorem. So given surface integral is now, becomes triple integral of divergence of f over the solid E, where E is everything inside S. So everything inside this paraboloid. But here, since the orientation is negative, you have to put the negative sign. So that's divergence theorem. If it's positive, you have to put positive sign. Okay, so that's it essentially. So all you have to do is just compute this double integral or triple integral, sorry. Then now, so for triple integral, you fix two of the variables first and integrate with the other variables. Now in this case, apparently it's easier to fix x and y for each fix x and y, and to be precise 0. You look above, and the first thing you hit is the paraboloid, and you go all over here, z is equal to 1. So the limits for z is from the paraboloid x squared plus y squared to 1. So for fixed x and y, your z value changes from x squared plus y squared and 1. Now, what's the divergence of f? Well, you just compute divergence. Namely, you differentiate each component by the corresponding variables. So in this case, you differentiate with x, you get z plus z and plus x dz and dA. So that's the integral you compute. And by the way, this gets cancelled out. So this is x squared plus y squared 1 x dz dA. And now let's just put d. We figure out what this d is, this part. Let's just take care of the innermost integral. Then now this is d. And since this is x and the variable you integrate with is z, so you get xz z is equal to a, oops, this is negative x times 1 minus x squared minus y squared dA. Then now, what's d? Well, this is double integral. Then now remember, once you take care of, for triple integral, once you take care of one of the variables, what you do is to project down everything on the rest of the variables. In other words, in this case, since you have taken care of the z-axis, what you do is to light up everything from the above, and you will see the shadow of this solid on the xy plane, and that gives you this part of the disk. Let me just write it down. So the shadow, and that's d, shadow is d, but in this case, it looks like this. X, y, like this. Now what's the radius? Radius is 1 actually. The reason it's 1 is because if z is equal to 1, you just plug in here, and x squared plus y squared is equal to 1. So it's just a circle like this. So use polar coordinates, you get x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared, and r is between 0 and 1, and then theta is between 0 and pi half. And of course, dA is, I forgot to mention this, dA is r cosine theta, I'm sorry, r, what am I doing? r dr d theta. So this is written as negative by polar coordinates r cosine theta times 1 minus r squared. Then now times r dr d theta, where r is from 0 to 1 and theta is from 0 to pi half. And this can be written as this. So you can separate for each variables, you get r squared minus r to the power 4. So those are for r. And for theta, you get cosine theta d theta. And then if you work this out, you are supposed to get 2 over 15. So that's the answer. Okay, so that's the end of the solution.